briefly recapitulate what we have done yesterday. So I claim that the strongest point of Hamiltonian mechanics is actually a possibility to exploit these canonical transformations. So there are special transformations which preserve the form of the Hamilton's equations, and you can think about it like similar, like having inertial frames for Newton's law or whatever. So really now I can consider transformations. So I introduce new capital Q and new capital P, which are functions of the old coordinates, such that there exists a Hamiltonian H prime, which need not be the original Hamiltonian, provided that the canonical transformation actually explicitly depends on time. So if the function, generating function, does not depend on time, H prime simply equals to H. But anyway, so there exists H prime such that the form of the Hamilton's equations is preserved. And so that's the definition which I'll be using. So now what is true is that such transformations, so not every transformation is canonical, as we have seen yesterday as an example. They are in one-to-one correspondence with things which are generated by this generating function. So for every canonical transformation, there is a corresponding generating function and vice versa. So now the statement is generating function is something which depends on an old coordinate, on one old coordinate, and for each old coordinate there is a new coordinate as well. So my choice was Q and capital Q, but you can also do, I don't know, P and capital P and whatever. You have 4 possibilities, and in general they are connected by Legendre transformation. So now let's use this choice. And so let's exploit the freedom in the Lagrangian description. So this is your Lagrangian here, and now I am free to add this function, the total derivative of a function of Q. All right, so now I do that. So I write this differential explicitly. So it's df over dq, q dot, df over d capital Q dot, and group the terms together. And so you have the terms q dot times something, and then something times q dot, and then this term here. So now you want this to be of the form capital P, capital Q dot minus H prime, because if it's in this form, and I use the variational principle, of course I get these Hamilton's equations, right? So this is what I really require to preserve the form. I require this. And then you get these equations of motion. So now, doing mathematics, I'm just comparing term by term. So whatever stands in Q, small q dot, doesn't appear here, so it has to be 0. So I derive the first relation that P is df over dq. Then whatever stands of capital Q dot has to be P. And so I have P is minus df over d capital Q. And then whatever remains has to be H prime. And so given the generating function f, this gives you the corresponding canonical transformation. Are there any questions to this? So now there was a question yesterday by Alicia whether the Lorentz transformations are canonical transformations. So I don't want to go to relativistic setting, but you may be asking a simple question. So in this non-relativistic setting, are rotations canonical transformations? And so it will be up to you to show this, that they are. Okay, so in today's tutorial, you will show that actually rotations are canonical transformations. And so, yeah, if you generalize this to relativistic setting, I expect that the Lorentz transformation will also. Anyway, so here I'm not doing anything this time. So here time is fixed, and I'm just changing Q and P. Yeah, that's the non-relativistic setting. Questions? All right. So now I didn't want to talk about this at all, but you forced me yesterday, and because we started it yesterday, let me finish it. So let me show these geometrical things, and maybe they will make some things clear. So what I was claiming yesterday is that given any space function, let's call it G, the Hamiltonian mechanics actually give you very, very strong tools to do something with this function. And so in particular, you take just this function g, and you may turn it to a differential operator, which is simply given by your Poisson bracket, where you leave the first slot empty. Okay, so if you write it in the, this is the canonical Poisson bracket as I defined it yesterday, and so whatever I should be differentiating here, I just leave that spot empty, and so then this is dg over dpi d over dqi minus dg over dqi d over dpi. Okay, so obviously this is a differential operator. It's a directional derivative. It tells me the direction in the phase space, if you want, in which I am differentiating. So now we shall see in general relativity course is that these directional derivatives are in one-to-one correspondence with vector fields. This is how you should be thinking of a vector field. So in flat space, the vector field, well, typically people think about it like numbers. So you have Cartesian basis, and then you say my vector is that long in this direction, that long in that direction. So this is the same thing. Okay. So now I'm saying that this is in one-to-one correspondence with the corresponding vector field, and then I'm saying that you can also write it as a time derivative with respect to the time generated by this function g. So the corresponding picture. So this is obvious. Right? You just have to believe me that this is a vector field. Well, what else it would be? This tells me which direction I move. Which direction I move. So this is basically the basis. In the simplest case, I will be moving in the x direction, and so, okay. And this tells me how much I'm moving. So that's the how much I move, and that's the components of the vector. Right? So typically just think about components in the Cartesian basis, and similarly here. So this is another basis, and this is another component here of that vector. So in other words, if you have your configuration space, then at each point of that configuration space, you have the vector xg. You have one here, you have another here, and of course this is everywhere on that configuration space. So the vector actually does not live in the configuration space. It lives in the tangent space, as you know. So if you take a sphere, you know that if I want a vector in some direction, that vector actually points out of the sphere. So it doesn't live in the sphere. It actually goes out of the sphere. So the vector lives in its own linear space, which is the corresponding vector space, which is tangent to that point, to my configuration space. And similarly here, right? So this guy lives in its own space. So now it's a fundamental theorem of differential equations, is that I can actually connect these points, provided that the vector field is sufficiently smooth, and by definition it is. So I can always find a curve so that at each point, the vector is actually tangent to that curve. Okay? And so this is my curve generated by my function g. Okay? So this is what's going on. So let me just plot it in a slightly different way. So I have my q and my p. This is my phase space. And then I have this curve gamma g here. And it just swipes some trajectory in that phase space. But of course, here I just plotted this for one particular curve. But the vector field exists everywhere on that configuration space. So actually, I have lots of these curves, and they simply foliate, they simply fill my phase space. So let's choose one of them. So this is my gamma of g. Okay. So now, choosing one particular gamma, I have chosen this one here. Well, that's my favorite representation gamma. You want to parameterize it where on that curve you are. And you do it by one parameter. Let's call that parameter tg. Okay? So then tg let's say I'll say Tg equal to 0 here, and then as I increase Tg, I simply swipe this curve here. Okay, so there will be Tg equals to 50 on whatever. So T is simply the parameter which parameterizes my curve. And that parameter, you can think about it like the time. So basically, you can say at time equal to 0, I am here in the phase space. And at time equal to 50, I just drag along this curve, and I get here. And at time equal to 100, I'll be here, and so on. So you can think about Tg as the time flow in the phase space generated by G. And so this explains now all these equalities, right? So this equality is trivial versus still trivial. This I'm telling you, you just be thinking about the differential operator as actually a vector. Okay, that's how the vectors are actually introduced in general relativity or in differential geometry. And then I'm saying you can also think about it like a time flow in the phase space. And this is precisely this picture here. Okay. So more terminology. So Pg is just the time flow, and then the corresponding vector field, which actually lives on this configuration space, has its own name. In honor of Hamilton, it's called Hamiltonian vector field. Vector field or vector flow, doesn't matter. Let's use. We don't have fields yet, so let's call it vector flow. It's more physical of G. So again, I have to know what my G is, and then I know what the corresponding vector actually looks like. Okay, so now it is obvious from this, what I'm saying here is that Hamiltonian is just a phase space function, right? So is this function G. So Hamiltonian is not any special at all. So Hamiltonian is simply one choice of the phase space function. And so you will say that Hamiltonian produces time evolution, but any function will do. Okay, so true Hamiltonian which generates true time evolution, H is not special at all. At all, except that people don't write TH, right? Except people write T equals to TH. Okay, so that's the only difference. Yes?
Is it true that given any phase space function G, you can always find a generating function F such that H
yes.
time equals G?
Yeah. All right, so are there questions about this?
But if I consider special relativity, then will it be special?
Then it will be
because you have a special direction that is different from other directions.
You have a special direction, meaning you have causality, or?
You have the minus sign in the matrix.
Oh, I see. Yeah, so you have some kind of causality. From this point of view, I would say no. Yeah, I would say no from this point of view. It's just no. I think no. So anyway, so now once we have this geometrical picture in mind, then it's obvious that if I take the Poisson bracket F and G and go through this equality and end up here, then all I have to do is to plug F here, and so it's dF over the dg, and it's just time evolution of G. Time evolution of F in this time tg, right? So in other words, so I have the function f, again, everywhere in the phase space. And then what you are basically doing is that you are interested in how f changes. So I have f at time equal to tg equal to 1. And then you are interested in how that f changes when you move here. F at tg equal to 30. Right? And so that's what's described here. So it's df over dtg, how the value of f changes as you drag it along that curve. Right? So that's what's going on here. So now, of course, this thing here just tells you the difference of the values of f here and of f here. But it's completely coordinate independent. It doesn't matter how I parameterize p and how I parameterize q. So this is a geometric quantity. Right? So I just take so for example, on Earth, I measure the temperatures, right? And so I measure one temperature in London and one temperature here. And so the difference of the temperatures will not depend on how I parameterize whatever the latitudes or longitudes and whatever. So it's just so this is a physical or geometrical quantity. Geometric quantity, and so it's independent of coordinates. So this thing shouldn't really change if I do any transformation of coordinates q and p. Okay, many questions. You were first, I think.
Could we say that the only difference between the Hamiltonian and any other g in phase space is that the parameter th of the Hamiltonian happens to coincide with our empirical notion of time? Would that be?
If you want to put it that way, yeah, maybe that's fine. But I'm saying, yeah, it's just you can choose any function in the phase space to be a Hamiltonian.
Yeah, things in order in my head. So could we say that?
I think you could, but it doesn't help you. Yeah.
This last comment that the bracket is independent of coordinates, is that only true for canonical trends?
Aha, very good. So this is a very, very good question, and so maybe I didn't explain it yesterday very properly. So okay, so this thing here is a geometric quantity. It really depends on the difference of the values here and difference of the values here. Doesn't depend on what coordinates I use. So no matter which coordinate transformation I do, even the non-canonical one, this thing will still be geometric quantity and will not change. What will change is the form of the Poisson bracket. So remember when we were deriving that df over dt normal t is equal to fg, we actually just differentiated, right? So we were using so when we, oh no. So when we first shown that df over dt normal t can be written as fh, and then let's not have explicit time dependence. So what we used is that this is, what is this? So this is df over dq q dot, df over dq q dot, plus df over dp p dot, and that's it, right? And in order to write it as a Poisson bracket, we had to use the Hamilton canonical equations. We had to use the q dot is dh over dp, right? dh over dp, and then p dot is minus dh over dq. So this is what we had to use. So we had to use the explicit form of canonical equations, right? So now then you can write it in this form. However, if you do an arbitrary transformation of coordinates, the form of the canonical equations will change. And so, well, the form of the Poisson bracket.
So the canonical equations also work for other functions than just the Hamiltonian case?
Yes, yes,
Right.
yes. Yeah. So the statement is that this is a geometrical quantity for any transformation. You can do any transformation, but canonical transformations are special. Canonical transformations are special because they preserve the form of Poisson bracket. So in other words, if I have f and g, I can calculate it in terms of the old coordinates. So that was given by my canonical Poisson bracket, df over dq, dg over dp, minus df over dp, dg over dq, right? So this is what we started with. And the statement is, if you have canonical transformation, but if and only if, you can also write it in terms of the new coordinates. And it will have exactly the same form. And this is if and only if you have canonical transformation. In all other cases, I can do some other transformation, but this will be something much more horrible.
And this is all based on the assumption that this Poisson bracket is equivalent to the vector field. Did we show that they are equivalent, or did we just assume?
Well, I was sort of arguing that they are. So really, the only thing which may bother you at this point is this one-to-one from differential operator to xg. You will see in relativity that's precisely how we define what we mean by vectors in curved space. So it's basically by postulate it is the same thing. So yeah, yeah.
Okay. For example, if I look at that diagram of P and Q in the second row.
Yeah.
For example, if we think of rotations, then it will be just the rotation of the axis, and we have the new P and Q, right?
Mm-hmm.
But what does it mean in general, geometrically, for canonical transformation?
What does it mean? What?
I mean, what does it mean if I do a canonical transformation? What is the meaning of changing the coordinates? Geometrically, what is preserved?
Okay. So geometrically, what is preserved is the symplectic form. so there is an internal structure to your phase space, which basically defines your Poisson bracket and stuff like that. And so this is a tensor, and so any transformation which preserves the tensor is actually canonical. That's geometrical point of view. But for us, it's really whatever keeps the Hamilton's equation the same, or whatever keeps the Poisson bracket the same. So that's a canonical transformation. So specifically, just a second. So specifically, this will be true for the fundamental brackets, So now you have, of course, if I calculate QQ and use this prescription here, well, obviously that's 0. If I calculate PP, obviously that's 0. And if I calculate QI and PJ using this thing here, that must be delta IJ. Okay, so if I calculate it using capital Q and capital P, this is obvious that it must be true, right? However, I may be stupid or clever, depending on the point of view, and to calculate these things in terms of small q and p, right? So I can also calculate them in terms of small q and p, and then this is highly non-trivial, right? So you get some differential equations, how q actually has to behave as a function of q and p, and how capital P has to behave. And so you get some conditions so that this is true. And the statement is these conditions are precisely equivalent to the fact that the transformation is canonical. It's canonical. So this is the simplest way how you check whether the given transformation is canonical or not. You just check the fundamental Poisson brackets in terms of the new coordinates, but you calculate them not in terms of the new coordinates, but in terms of the old ones. And that gives you conditions, and either they are satisfied by your transformation or not. If they are satisfied, your transformation is canonical. That's the simplest way how you can tell whether the transformation is canonical or not. Another way is to find the generating function. That's typically much more complicated. Right? So here I just have to differentiate. To find the canonical, to find the generating function, I have to actually integrate. Right? Yes?
This way, is there a quick way to get h prime?
To h prime? Well, okay. So if you just concentrate on the transformations which don't involve time, which is typically the case, so people don't typically, it's just equal to h, right? So if you want to find h prime and your transformation depends on time and stuff like that, then yeah, you need to go through finding the generating function, I would say.
Is it better to take the definition of the Poisson bracket to be df dtg instead of the what you have over here at writing?
Okay, so
because if for a non-canonical transformation the Poisson bracket is still defined.
You can do that. I think so. Yeah, that will be more invariant, and of course then it only reduces to the standard form of Poisson bracket in certain cases. Yeah.
So I just wanted to check when we said that the true Hamiltonian h is not special. Does that mean that if we write the action as being an integral over tg and use our function instead of a, is that still obeying the action principle then?
Well, you may impose that it does, right? So all I'm saying here is that you should be thinking of Hamiltonian as just one concrete choice of some phase-space function, right? So it's just a phase-space function. That's all I'm saying, right? It's not special in any way. It doesn't have extra other property. It's just say I choose this space-phase function and I call it Hamiltonian. And then this gives my true time evolution, right?
What if we have functions of the phase space that take elements in the phase space but take it to a vector space? For example, angular momentum or something like that. That f or g are actual vectors.
Right.
Not scalar functions.
Okay.
So what would we do in that case? Would we decompose in components and do this Poisson bracket or what?
Yeah. So you would do it component by component, and you will do it tomorrow. All right. So we have that. So now I haven't really proved this, but it's sort of obvious from what I was saying here that I really need the canonical form of Hamilton's equations in order this to be true. So if you don't believe it, do it yourself. This is DIY in Canada. So anyway, so now because we have all this nice geometrical picture, let me discuss the Noether's theorem, which is really beautiful in Hamilton's theory. So now you define a symmetry of phase-space function g, provided that gf. Okay, sorry. So you say that. Let me say it. It's the full sentence. So flow generated by phase-space function f is the symmetry of another phase-space function g, provided that g of f, which of course is dg over dgf, is 0. Okay, that's a terminology, it's a definition if you want. So in other words, as I flow along my f curve, g does not change. So g has the same value as I flow along the curve. Okay, everybody happy with this? So as I flow here, and g1, I have g2. This is my gamma of f, and then you know that g1 equals to g2, and that will be true along that curve.
And the Poisson bracket is antisymmetric, so that would also happen like in the opposite.
Exactly. So that's the Noether's theorem. You just discovered the Noether's theorem. So Noether 4, version 4, which is the Hamiltonian version. Very good. So let there be a symmetry. be a symmetry of Hamiltonian H, generated by phase space function I. Okay, so now I'm not using G or F, I'm just using I. So this is my phase space function. So then the statement is I is your concept quantity. It has the most beautiful version of Noether's theorem. Of course, the proof is just 2 sentences. So proof of this. So you know that HI, which is dH over dTi, is equal to 0 by assumption. In other words, you are saying that the Hamiltonian is preserved along the flow generated by function I. But then the Poisson bracket is antisymmetric, right? So then also this is true, IH, which however now is di over dTh, but I don't write h, must be 0. And that's certainly true by antisymmetry of the Poisson bracket. And that's the proof. So if you go and understand Noether's theorem in this way, so of course what it's saying is quite non-trivial if you start drawing pictures, right? So if you have P and Q here, so then you will have one flow generated by your function I. So these are the curves generated by the function I. And so you have T of I flowing here. And then you have another flow generated by your true Hamiltonian. So it's gamma H. And that's the real time. Right? And so the statement is, and it's just guaranteed by the antisymmetry of the Poisson brackets, is that you know that if the Hamiltonian is preserved, so if I move along this curve, for example, and I have H1, and then I move over here, and I have H2, so the statement is if H1 equals to H2 for all the points everywhere, then if I move this direction, and I have some value I1, and then I2, then they will be also the same. I1 equals to I2 for all the points in the phase space. And this is quite interesting, right? That it follows just from the antisymmetry of the Poisson bracket. Very good. More questions? So this is something I didn't want to discuss at all, but I think it's beautiful. So, and you asked for it yesterday, so, okay. So that's really the geometric picture you should be thinking about for the Hamiltonian mechanics. So now I'll tell you one more shocking statement, which in terms of this thing is not really shocking. So as somebody asked me, so I have this flow generated by any function, and then they asked me, is this flow, does it correspond to some canonical transformation? And I said, yes, it does. Right? So any flow which is generated by this, by a function, phase space function, actually is a canonical transformation. Okay, so you can be thinking about it like I start here. I start here at some Q0 and P0, and then as I flow here, I have some new Q and new P. And that's my time evolution. I am evolving from Q0, P0 to Q and P. Right? And the statement is So I'm changing Q0 to P and P0 to Q and P, which is a canonical transformation, provided this flow is generated by any phase space function. That's the statement. Of course, this is true in particular for the Hamiltonian and for the true time evolution. So it shouldn't be surprising that time evolution is canonical transformation. For information, so P and Q. Now I have the true time evolution generated by gamma H, and I simply go from Q0 and P0 to some later Q and later P. And so I'm transforming Q0 and P0 to Q and P, and that's a canonical transformation. All right, so that's good. And it shouldn't be surprising from what we just said here. So now, in this case, I can even give you the generating function, which means in all other cases, you can actually get the generating function as well. And so the statement is this is generated by generating function f equals to minus s. So now, of course, there is not enough letters in the alphabet. So we already use s for the action. So now a stupid idea to use s again. However, maybe it's not that stupid. The statement is that this generating function basically is action, but not entirely. So it's action when evaluated on shell. So what this s is, and I'm sure many of you, so s is called Hamilton's function. It's crazy, everything is Hamilton, right? Hamilton's function. And this is basically the action on shell, which is a function of coordinates and time. So this is very vaguely. So that's why s. Okay, so what is it you have to do? Is that you have s, which is a functional of q, and that's L dt, right? So that's how we started our discussion. So we have the functional s, the action s, that's given by L dt here. So then we vary this action. So then you vary this action, and you get the Euler-Lagrange equations. Euler-Lagrange equations, which are dl over dq minus d over dt dl over dq dot equals to 0. So by the way, this action is from 1 to 2, from t1 to t2. So now you have these Euler-Lagrange equations, provided you can solve them. Okay, so provided I can solve. So the procedure how to get this Hamilton function is to solve the Euler-Lagrange equations and express the solution in terms of the boundary data. In terms of boundary data values. So of course, so your Euler-Lagrange equation is just a second-order differential equation. So if I'm just in one dimension, it has two integration constants. So the statement is, if I impose the boundary values, meaning at t1, I am at fixed q1, and at t2, I'm at fixed q2, you can express these integration constants in terms of these T1, Q1, and T2 and Q2. So if you do it, you have Q as a function of T1, Q1, T2, and Q2. Okay, so this is how you just plug in for your integration constants these boundary data. Right? So that's the first step. Second step is to plug it back to Lagrangian. So plug back to L and integrate and evaluate S. So what you are really doing is now your S will be a function, not a functional anymore of your trajectory, but it will be a function of your boundary data. It will be a function of T1, Q1, T2, and Q2. And how it is obtained is that you integrate from T1 to T2 your Lagrangian, which is now an explicit solution, so L, where Q is Q, T1, T2, Q, Q1, Q2, dt. Right? So I just plug for your Lagrangians. I take 1/2 mv squared. I know what my v looks like in terms of T1, Q1, T2, and Q2. So I get an explicit expression, and I integrate it over. Okay, so there's also time over time t. And this is, so there's also t here. This is q of t, so it must depend on t. And this is how you get the Hamilton's function. All right. So who has calculated Hamilton's functions before? Some people did. So if you have taken, so this is very important quantity in quantum mechanics and quantum gravity and other things. And basically the statement is once you know this function S, you know everything about the motion you can wish for. So it's actually fun to calculate these things, and you will do it today for some simple mechanical systems, just to see what this thing is. So why is it actually interesting and important? Is that you can show, and I will not show it, but you can read Landau and Lifshitz if you want. It's like 2 pages of discussion. You can show that if you take a different, so this function, the Hamilton function, is a function of T1, Q1, T2, and Q2, right? So now I can take a total differential of these things with respect to T1 and T2 and Q1 and Q2. So then the statement is, so Landau and Lifshitz, I don't know which page, but it's almost obvious. Okay, so then if you take the differential here, so why is this obvious? This is not a proof. It's just why it is obvious. Is you know that your action is just p q dot minus h, right? And you integrate that and you plug in the solutions or whatever. So now compare with this, with what I'm saying, you just have to take a differential now of this thing. And what you find, and this is pq, p dq minus h dt at time t2 minus p dq minus h dt at time t1. Okay, so now, so this is dq2, this is dt2, that is dq1, dt1. Okay. Is this? So now I don't know if I have the signs right, but let's hope. So let's call so okay, so let's not do that. So the statement is this equation here just tells you, for example, interesting things like ds over dq2 gives you p, or ds over dt2 gives you h, stuff like that. So it gives you energy and stuff like that. So you will explicitly verify these relations in your tutorial and basically verify that in particular case this is true. So now let me integrate this relation. So now if you put an integral back, and arrange the terms, and I will call which one is which one, doesn't matter. So let me put this thing. So integral over ds, and then at time t1, let me put it here. It's plus t1 dq1 minus h1 dt1. That's on one side. And this is equal to integral p dq, p2 dq2 minus h2 dt2. Okay. So now, if I rename, oh, this is my initial thing, right? So I have my initial data are q1 and t1, or q, q, and whatever. This is my initial data. And this is my final data. So this is true for the point 2, but it's true for any time as well. So I can actually delete the 2 here. And so now you see that whatever is written here is precisely what I was writing over there. So I have the action, which is whatever pq dot minus h minus df over dt. That's what's on the left-hand side, provided that I identify f to be minus s. Okay, so this actually shows that this thing s here is the generating function of that of the transformation, which takes you from q1 to q and t. Right. So now I have a canonical transformation which takes you from the values here, q1 and t1, to some arbitrary values q and t. And that canonical transformation is generated by f equals to minus s, because it's there. So just comparing this is whatever we are doing above. So that's Landau's argument. And of course, the result is correct. Question?
So, like in the picture, basically the transverse flow is Ts.
So the transverse flow why would be a transverse flow?
Just like
I mean that flow. Yeah, that's the Hamiltonian flow. Yeah.
So like evolving with Ts just gives you other physical trajectories with different boundary conditions, basically.
Yeah, so the statement is, I start with precisely what I'm putting here, right? So I evolve along my time evolution, and I start with some boundary data, q0 and p0. I take it as my old coordinate, and then I can think about the time evolution as taking me to a new q and p. So sorry, I am using 1 and 0. So 1, of course, is 0 here. And it's taking to q and p, the new ones. And the statement is, this is just, drag along the time flow. And it's a canonical transformation. And it's canonical transformation generated by this Hamilton function. OK. Last thing I want to discuss about the Hamiltonian mechanics is the Liouville's theorem. We will see another one later on. And that basically, so of course, if you have just one point or one system, it's corresponding to a point in the phase space, and now its time evolution just sweeps a trajectory in that phase space. So now in the statistical physics, where you sort of talk about many things, you sort of spread this point, and you have a volume occupied by a system because there is some uncertainty and stuff like that. So Liouville's theorem actually talks about this. So now the statement is volume of the phase space, and you will use this in statistical physics to basically derive the Gibbs distribution. So there's like 2 lines from this theorem to Gibbs distribution. So volume of the phase space remains invariant. Under canonical transformations. Meaning it's in specifically by time evolution. So the picture is, in statistical physics, you don't talk about one point in the phase space, but rather you talk about many points, and so I like this cat picture. So that's your cat here. And so this is my volume of the phase space at time equal to, this is really ugly, sorry for that. So there's at time equal to t0, we have some volume in the phase space, P and Q. And then each point sort of evolves according to Hamilton's equations, right? So now you have the time evolution. And what happens is that the cat gets squashed. So that you don't recognize that it's a cat anymore, not that you would in the first picture. Okay, so that's the time evolution. So this is volume at time t. So time evolution. So, you know, the pictures get distorted and whatever, but the volume actually remains the same. So the statement is that the volume at time t, of course, this is just a canonical transformation. Time evolution is just a coordinate transformation. So at time t, I calculate it in terms of my new variables dq and dp. Okay. So now I want to change the variables to the old ones, but there is a Jacobian of the transformation dq and dp, where the Jacobian is just, in the simplest case, it's just dq over dq, dq over dp, dp over dq, dp over dp, right? So it's a determinant of this matrix of the transformation. Okay, it's a 2x2 matrix, even I can calculate the determinant. So it's dq over dq, dp over dp, minus dp over dq, dq over dp. And so actually what this is just q and p. It's just the Poisson bracket of q and p. But the transformation is canonical, so the fundamental bracket has to remain equal to 1. Okay. So this is equal to 1. And so that's why this Jacobian is just 1. It's just integral over dq dp, which is my volume at time equal to 0. So that's the proof of Liouville's theorem in one dimension. So just remember, you know, as you evolve in time, you can, you know, twist things and you can stretch them and whatever, but in the end, the volume of the system actually remains the same. Yes?
I thought Liouville's theorem was more specific, like it was more about the projection on the planes, like on each plane of conjugate variables.
Maybe there are some more involved versions. I just taken. So this is enough to show actually Gibbs distribution, for example. So maybe there are some more. So first of all, Liouville was a very creative guy, and so we will discuss tomorrow Liouville's integrability theorem, which is something completely different to this thing. But he has done many things. But this is just the simplest formulation about the preservation of the volume. So maybe there are some refined versions. I don't know actually. I have to admit I have no idea what they are. Yeah.
Is this theorem for non-distributive systems?
Well, this is provided the Hamilton's equations actually are microscopically valid. So of course that doesn't describe the system. Yeah.
Just to be clear, you're saying that the time evolution is a canonical transformation, right?
Yeah.
And that's why you get the...
Yeah, exactly. All right, so I have 15 minutes for the Hamilton-Jacobi equation. Hallelujah. We can do it. And the reason why we can do it is that everything is already here on that blackboard. All right, part D, Hamilton-Jacobi theory. Now we will use these canonical transformations to do something amazing. So if you look at, so after the canonical transformation, I'll put it a little bit more down so that you don't have to look that much up. So after the canonical transformations to nu q and nu p, you have this new Hamiltonian H prime and this form of the Hamilton's equations. And then we have also, these relations for the corresponding generating function. All right. So now, what was an ingenious idea of these two gentlemen is that, well, maybe I can actually kill the time evolution completely by doing a canonical transformation. Maybe I can transform to a system where my new Hamiltonian H prime is equal to 0. Okay, so this is like really crazy idea. But of course, if I can do that, I can immediately solve the Hamilton's equations, right? And so I have solved the problem. Very good, so let's try to do it. So ingenious idea is to do such canonical transformation so that my new Hamiltonian H prime is identically equal to 0. Okay. Well, if I can do it, then Hamilton's equations are trivial. And I can actually write down the solution. So dH prime, of course, is 0 because H prime is 0. So Qj dot is 0. So Qj is a constant. Qj, let's call it alpha j, which is a constant. And Pj, and so is Pj. And let me preserve that sign. Minus beta j, which is another set of constants. So we have solved Hamilton's equations. All right. Well, that's fine. Doesn't still tell me how the motion actually really works. So to really solve how the trajectory small q and small p evolves in time, what you have to do is that you have to look at the second equation here. So now let's look at this equation here for the generating function. And let's pretend that we have found the corresponding generating function, which actually gives me this Hamiltonian H prime equal to 0. Okay, for the lack of letters, as I said already, lack of letters, let's call the corresponding generating function S again. Okay, F is S. Okay, that's the corresponding generating function. Okay, very good. So now we have the middle relation gives you that Pj is minus ds over the Qj. Well, Pj is just a constant, we just integrated it. So this is beta j. So remember, we had the generating function, which is a function of small q and capital Q and t. but capital Q we integrated to be alpha. Right? So it's Q and T. But this guy we already know it's alpha. So beta J is minus ds of Q and alpha and T divided by d alpha J. Alpha J. Okay, so that's the middle relation, right? I'm just plugging in whatever the solution of the Hamilton's equation we found. Okay, so now if you look at the, well, okay, the left-hand side is just a constant. The right-hand side has Q in it, it has constant alpha in it, and it has time in it, right? Even after differentiation. So in other words, this is an implicit relation for Q as a function of time and two integration constants, alpha and beta. So this is an implicit relation. Implicit relation for Q written as a function of alpha, beta, and T. So if you want two integration constants. So this is a solution of the problem. Yeah?
Is Pj minus beta or?
Sorry, I put a minus, thank you. So I put a minus here, minus beta j. So then we have DSO, yeah. Thank you. So if I can actually invert this, so I have beta equals to some function of Q alpha and T. So if I can invert this, I will have Q as a function of alpha, beta, and T, which is my solution I'm after, right? I want this to be a function of two integration constants. Right? And so we are done and we can celebrate. Celebration. Okay. Well, not quite. Not yet, but soon. We still don't know what S is, right? So at this point, it was just a generating function, which I said, well, this generates H prime equal to 0, right? So we are almost done, but we need to know what S is. So how to find this miraculous S? And the answer is, well, we haven't used all the equations we have in our dispose, right? We have used the Hamilton's equations, and we have used the middle equation over there. But we have still the first and the third equation to use, right? So using the third equation, we require that H prime is equal to 0, which is H plus ds over dt. So now H is a function of Q and P and whatever. So it's H is a function of Q and P and T plus ds over dt, right? So that's from the third equation. But we have still one equation left. That's the first one. And that tells me that small p is given as a derivative of S with respect to Q. Okay. The statement is this thing has to be given by ds over dq. So now this is it. So we arrived at an equation for S. So we used all the equations, so now the problem has to be solvable. And that's the right track to do. And so we find that our function S is simply given by a solution of this equation, which I wrote down. So let me write it again. So S is a solution to equation ds over dt plus h, q, and then in terms of p, I write ds over dq and t and this is equal to 0. And that's the famous Hamilton-Jacobi equation. And so you see that we have done quite a journey from Newton. I didn't really discuss, but you start with Newton, then you go to Lagrangian description, where you have second-order differential equations, Euler-Lagrange equations. Then you go to twice as many Hamilton's equations, and suddenly show that actually all the mechanical systems, so all those equations were ordinary differential equations, they were just equations in time. But now the statement is this is completely equivalent to just one equation, but now this equation is not ordinary differential equation, it's a partial differential equation for my function S, which is a function of Q and T. Okay, so you just traded all these 2n Hamilton's equations for just one PDE, which is a function for function S, Q of T. Yes?
Isn't it also a function of alpha?
Okay, very good. So the statement is, this is your equation. All you have to do to obtain this equation is take the Hamiltonian, everywhere you see P, plug for it ds over dq, right? And then add this ds over d term. This is an equation for Q and T. So now the statement is, if you solve this equation, it will depend on the right integration constants. It will depend on these alphas. And then you can use this procedure here, and you can differentiate that solution with respect to the alpha, which is an integration constant. You set it equal to another constant beta, and you have the solution. All right. Are there any other questions? So you want to solve this Hamilton-Jacobi equation, and what you are interested in. So you want a solution that depends on the right number of these integration constants, which is of the form S, Qi, alpha, I, and T. But these are the integration constants. And you want, of course, that there be that many integration constants as you need. So n integration constants if you have n degrees of freedom. And so solutions to PDEs which contain these integration constants like that are called complete integral. So if you studied some PDEs, for example, the wave equation, you know that one solution of the wave equation is an arbitrary function of x minus vt. Okay, so that would be a solution which is called a general integral, and it doesn't depend on any integration constant. It just tells you the answer. The anything that solves the wave equation is some function of x minus v. So that's not the solution we are after. We are after a solution which contains these integration constants. That's a different type of solution. Okay. So now, how to get it? So get this, and the answer is it's difficult, as with any PDE, right? But surprisingly, many interesting problems can be solved by a method of separation of variables. So you can try separation of variables. And so then there are cases when it's actually guaranteed that it will work. So what I mean by separation of variables, so your function depends on q, but of course I have many q's, right? So it depends on x, y, z, and whatever t. Okay. So now what you are trying to do is that you are trying to separate the full thing into something which depends only on x, for something which depends only on y, for something which depends only on z, for something which depends only on t. Okay, if you can do that, plug it into the equation, typically you just get normal differential equations for these Sx, Sy, Sz, and so on. Okay, so now the statement is if the Hamiltonian is not explicit function of time, then you can search for, well, then it's guaranteed that you can write it as S0 Qi minus Et. So if Hamiltonian is does not depend on time, the time coordinate separates, but it's even better than that. It's just linear in t, and whatever stands here is the integration constant. Integration constant. I wrote E because of the lack of the letters. What do you know what E is? E is the energy, exactly. So you can show that this is really has the if Hamiltonian doesn't depend on time, the energy is conserved. It's a constant of motion, and it's precisely what occurs here in the separation method. So similarly, if H does not depend on some cyclic coordinate, it doesn't depend on some concrete QC, then you can write as Qy t to be the corresponding constant alpha c QC plus the rest, where this is Qi different from QC, right? So again, so if let's say my Hamiltonian doesn't depend on x, then I can always write something linear in x times the corresponding integration constant. It doesn't depend on x. What is the interpretation of this integration constant alpha c?
Momentum.
Momentum, exactly. So this would be the momentum. Okay. So in general, you may try. In general, try just an additive separation. You just write S of Qi to be a sum over I, Si. Okay, this is stupid. S, Q1, Q2, and so on. Si, Qi, meaning I have Si depends only on Qi. So you may try this additive separation ansatz. There's S1, function of Q1 only. S2, Q2, and so on. So you may try this ansatz. In most of the cases, it will not work. But there are some cases when it will work, and it gives you the complete integral, and then you can integrate motion. Okay. So now there is a caveat here. You may spend your lifetime trying to separate Hamilton-Jacobi equation for one system, right? And the reason is that whether this separation thing, whether this additive separation ansatz works or not, depends on which coordinates you choose, right? So it may be the case that the system separates in Cartesian coordinates, or maybe not. Maybe it separates in spherical coordinates, or maybe not. Maybe it separates in something else, right? And so not being able to separate your equation doesn't mean that actually there is no other coordinate system where you can separate your equation. So be careful not to do this forever. Try forever. Because there's basically no algorithm to find which is the right coordinate system where your equation actually separates. And of course, you don't know whether such a system even exists, right? So, but if you can find a coordinate system where it separates, then I have the complete integral, and then I solve the motion. And actually, this is how quite many integrable systems were discovered in the past. Is that this is the most effective method of finding integrable systems, is that you really try to formulate this Hamilton-Jacobi equation and try to separate it. And that's how you find these integrals of motion, which you typically have no idea that they did exist, right? And so that's how people actually found integrable systems in the past. All right, so I have no time to discuss an example, so I'll discuss the example tomorrow. It would be a very, very simple example of a free fall in a homogeneous gravitational field. And then, so I can do only simple examples, and then you will do much more complicated example in your tutorial tomorrow. Okay, so let me stop here. Questions?
Jake, so alpha C, you said was the momentum, but up here, the momentum was assigned to beta. Is that?
Oh.
Checking out.
Yeah. So this is a different alpha. It's not an alpha. Is it alpha? What is it I'm doing? Q.
Gamma.
Q alpha C. I'm doing something strange. So anyway, so what I mean here is that let's call it something else. Let's call it P. Okay, that removes the problem, right? So, but what I'm saying is, well, P is not good. But anyway, so it's an integration constant. It's a constant here. Okay. Other questions? Okay, so see you in the afternoon.